So this week we're going to move on a little bit from what we've been doing for the past month or so, where you've been doing this chapter 3 in your notes, all about how to get to posterior distributions from a prior. We're going to move on this week to talk about chapter 4, which is all about prediction. So we'll just recap how this is going to be different from what we were doing last week. So in terms of what we were doing before, we always had some form of distribution for some data that we had. And we could write that from some standard distribution that we knew about. And the thing that we were concerned with learning about then was what these unknown parameters were that describe the distribution, the family of distributions that our data belongs to. So when we talked about normally distributed data, we were talking about something like the mean of this distribution, and we also did an example where we talked about the variance. And when we talked about binomial data, we're thinking about theta, which is this parameter of the sort of probability of success in these binomial trials that we're doing. So we want to learn all about this data given some observation, all about this parameter given some observations of our data. So we did this whole process where we had some sort of prior distribution for our parameter. And most of the time we were talking about this being a conjugate distribution so that it would make things easier when we go to a posterior analysis. But we also talked a lot about what we would do when we had weak prior knowledge. And then we did this posterior analysis where we worked out what this distribution of our parameter was once we'd seen our data. And we used Bayes' theorem then for that. And then the only other thing that we might do once we've got this posterior is we might look at some derived quantities. So we looked at things like what our posterior mean was, or variance. And we can do things like we could compare them with what our prior mean and variance have been. But that was as far as we got to in terms of giving this information back to somebody. So say we had a situation where we have somebody that knows something about this parameter, this expert that we would use to get this prior elicitation. So they might give us some information that they know about this parameter, what they expect it to be, how much they maybe expect it to vary. And then all that we could do was go back to them then with some posterior expectations about that parameter. But that's not always that useful. So if you were actually going to take it to somebody that didn't have any awareness of stats, so if we talk about something like that example with the GM sheep, if they've done this experiment on the sheep to do with how many of their GM sheep are can no longer get whatever disease it was that we were talking about, and they might be able to go back to the scientists and give them things like these expectations and variances of our parameters. But if this GM company has made this groundbreaking discovery in their sheep and they want some sort of press release about that, you're not going to get a press release that says, oh, these sheep have this expectation of variance about how non-susceptible they are to this disease anymore. You're going to actually be talking about how many sheep we would expect to get them. So when you're talking to something like the general public, you don't want to talk about parameters anymore because the general public don't know about parameters. You want to talk about what things that they can actually observe, and they can observe data. So in the GM case, how many sheep are actually going to get the disease or aren't going to get the disease. So what we're going to talk about today is all about, and tomorrow, all about what we can do, how we can speak about future observations. So if we've already had this data X, and we've used that to learn about theta, what happens when we have some new data Y? What can we say about Y, data that we've maybe not collected yet, but we want to go and collect? In the GM example, maybe we've got 10 more sheep, and we want to know how many of them are actually going to be susceptible to this disease or not. What can we say about that now that we've already seen our data X? So that's going to be all of what we're going to talk about for today and tomorrow. This is useful then because it's more interpretable to people. Talking about this parameter is more difficult than just talking about what the data might actually look like. I think we have an example in the slides as well of why that's the case. So if we have 2 treatments, 1 and 2, and we've got this theta being this parameter to do with the mean lifetime of people on these 2 different treatments. And you can get some data X, like we have done in all the examples that we've done. And then you can do some sort of posterior analysis to learn about what these parameters theta are to do with how long somebody's going to live after these 2 treatments. But reporting something like the probability that theta 1 is greater than theta 2, so these kinds of derived quantities are difficult for somebody to understand. Whereas if we just wanted to talk about the probability that a new person was going to live longer, given that they were on treatment 1 than somebody that was on treatment 2, that's something that we can relate to a little bit more. So like news stories that have come out recently, you have all that stuff like there was one this month about if you have an extra glass of wine a day, that's going to reduce your mean lifetime by a day or something. So that's the kind of thing where this crops up. They've not told you in that news story anything about theta, a parameter that they're working with. They're just talking about something that you can observe, your actual mean life expectancy. And they're saying that that's going to be drastically cut. So that's what we want to work with today. So if we're wanting to do that, the thing that we want to learn about then is this predictive distribution. So what is our distribution of y given that we've observed x? To do that, we need to make some assumptions about our data to do with independence. So we've been doing this all along in terms of our data x, but not really talking about it that much. So whenever we've had some data in the examples that we've been talking about, we've always assumed that they're independent, conditional on theta. And that's why we've been able to easily write down then what f of x was given theta in all these cases, because each of our x's, once we know about theta, are independent from one another. So we're going to have to assume the same thing here. So we're going to assume that if we already know what theta is, so the parameter of our distribution, so in the GM sheep case, that parameter theta, the probability that a sheep is susceptible to a disease or not, once we already know what this is, the data that we've obtained previously doesn't influence what we can learn about y. So once we already know what theta is, x doesn't matter. It doesn't give us any additional information about our new data y, because we already have this information about the distribution. So if we know that our data is binomially distributed, and we know what the parameter of that binomial distribution is, having some observations from that distribution don't tell us anything more about future observations of that distribution, because the parameter fully describes that distribution. It doesn't help us anymore having some observations from it. And so we're going to assume that this whole time. But what we're actually trying to work out is this distribution of y given x. We don't know what theta is at the minute. So we need some expression for how to work that out in terms of things that we do know. So we want to know about this distribution of y given x. And we know that things are going to be easier if we work with theta. So we've done this kind of trick a few times already, where we introduce, when we want to know about something, we introduce some variable that we that's going to make things easier for us, but all we're actually doing then is integrating over it. So we've introduced this joint distribution between y and theta, but we're integrating out over theta, so that's why we then end up with not having theta in this expression, and these two things are actually equal to one another. And the reason that we do this is because it's going to simplify to something. So we can write any joint distribution as something that looks a little bit simpler. So you'll all remember that we can do this joint distribution of A and B as that. That's nothing new. And in this case, we have something that we're conditioning on here. That basically makes no difference here. We can still work with this expression even when we have something that we're conditioning on. It's just everything on the right-hand side still has that conditioning. So we can still follow this process, but now every term is just also conditional on C. So we can do that over here. So we have our y can be our A, our theta can be our B, and then x is just this C that we're always going to condition on. And then this looks quite familiar because, and that's the reason that I've wrote it with a pi instead of an f, because that's our posterior distribution that we worked out in previous lectures. So we have our posterior distribution here, so we already know about that bit. And then if we look at this term, so we have this conditional distribution of y given our parameter on our data, and we've said that we're going to make an assumption throughout all of this course that our new data, y, is going to be conditionally independent to x given our parameter. So once we already know our parameter, x doesn't teach us anything new about y. So we already have our parameter, x doesn't teach us anything new, so we can just get rid of that. So we have our posterior. And this is going to be our likelihood of our new data given our parameters. And we'll have already seen what kind of form this has, because x and y, they're both coming from the same distribution. It's just x is the data that we've already seen, and y is the data that we haven't seen yet. But they're still all coming from the same distribution. So when we would have worked out what our posterior was earlier on, we would have worked out what this likelihood of our data x given theta was. And our new data y is still going to come from the same distribution. So we're going to be able to know what this distribution here is, and we can write that down. So we're going to have some sort of function for each of these two terms in our integral. So we're going to be able to write those when we actually have an example, but we have this integral that we're going to have to work out. So we're going to have to use this idea that we used last week, where we have to deal with difficult integrals. Again, I did say last week that we're going to have to keep using that. So we'll just have that up so that we remember what it is. Again. So this is this trick that we do to solve difficult integrals basically without having to solve them. So if we want to find out the integral of this function f of x, and that's too difficult to do, but we know that I'm going to use a g actually here. So we want to find out this integral g, but we know that g is a function of a PDF. So this is just going to be a constant. And f of x is a PDF. And we know that if f of x is a PDF, then the integral of this is going to be equal to 1. So the way that we can then solve this is that the integral that we want to learn about is just going to be equal to this. And because g is just a constant number, we can take that outside. And then we already know, because f is a PDF, that that integral is equal to 1. So we're going to keep using this approach to solve these integrals. So once we have this predictive distribution for y, we can use this trick to actually solve what that integral is inside it. So in terms of how this differs from what you might do in a frequentist setting, we'll leave that up for now. If you were to ever, we keep doing this thing where we compare what would happen in a frequentist setting to what we're now doing in Bayesian. So all of the examples that we've done previously, we keep doing this thing where we look at the posterior expectation, and we keep writing it in terms of things like the maximum likelihood estimator, which is what we would use if we were doing a frequentist analysis. And we can do the same here. So if you'd been given some data x, you wanted to learn about theta, the parameter of it, then you would use your maximum likelihood estimator of that parameter to estimate what it was. So in sort of a normal setting, you have some normally distributed data. You want to learn about the parameter that's the mean of that distribution. You get some data x, and you take the sample mean of that, because that's your maximum likelihood estimator for theta. If you were then going to predict some future observation of some new data y, then you would use that maximum likelihood estimate. So to get their distribution of what y is, they would just say, well, our parameter is just equal to what our maximum likelihood estimator of that parameter is. Because in a frequentist setting, our parameter is just a single fixed value. That's what we always assume. So we just set it equal to our best guess. We have no uncertainty in a frequentist setting on what this parameter is. It's just a number. So the best thing to do, therefore, would just be to use our best guess of that number at what it actually equals. So if you got some normally distributed data, say, and you have what your new data y could be, then you'd just assume that your new data, it's going to be normally distributed, because we're working with normally distributed data, but you'd assume that it was distributed then with a mean equal to the MLE. So you would get this distribution for y that's just a normal distribution with mean equal to what your maximum likelihood estimator was. So if we look at the expression that we have for our predictive distribution, they're basically saying here that if you were to look at this and you were to set this sort of posterior distribution, which we don't really have in a frequentist setting, but we can pretend that we do, where what a frequentist would set as their posterior then is just it's either 1 or 0, depending on whether theta is the maximum likelihood estimator. And if we compare what we have here with doing this, then we would only get a 1 here at the point where theta is maximum likelihood estimator. And then our predictive distribution then is the distribution of y given that maximum likelihood estimator. So that kind of shows the link between what we're going to do in our Bayesian setting and what a frequentist would do. And why that's different then is that they pick this single value and they have the distribution of the data with that as a parameter. In a Bayesian sense, we don't fix this parameter at our maximum likelihood estimate, we don't fix it at anything. We assume that we have a distribution over theta. That's what this posterior is. It tells us how likely theta is over different values. And then we integrate over theta, taking that into account every time. So we look at what's the distribution of y given theta, but we weight it by each value that we have or could possibly have for theta. So in a frequentist setting, they only weight that by this one value, their maximum likelihood estimator. But in a Bayesian setting, we allow all the possibilities that theta could be, and we just weight them by how likely each of them are. So it's taking more uncertainty into account, and that's why people might prefer it. But it is going to mean that our uncertainty about what y is going to be in the future is going to be more uncertain than what a frequentist might set their distribution of y to be. So this is what our predictive distribution is. We're going to spend the rest of today and all of tomorrow just doing examples on how to actually calculate this in different settings. We'll do quite a few examples. Today we'll talk about this binomially distributed data. So we're going to carry on this sheep example that we keep looking at. We might also have time to look at some exponential data as well. In terms of what other examples that you have in your lecture notes, you've got some additional examples that we won't go through. So you've got some normally distributed data examples. So that's going to carry on the pollution example that you keep doing. And you also have an example with Poisson data. So you should look through those in your own time as well. In terms of exercises for you to do on this, once we've done this binomial example today, you've got an exercise in the lecture notes in 4.3.1 that's going to extend that example. So after today, you can try that. And then you also have this example that you had exercise earlier on in the lecture notes, all about teachers grading students' exams. You take that example further and extend that to predictive distributions too. So we'll talk about this binomial data. So we still have this example where our data is binomial. So we have this x, which is the number of successes that we might observe in a given number of n trials. So in the past, we saw that you can take a conjugate prior for this parameter theta, which describes the probability of success in these binomial trials. And if we take a beta prior, then that's conjugate. So our posterior then is beta. And we've already worked out what the posterior distribution in that case is. So we have some data that's binomial. We know what this is. This is just the number of trials that we have, but we don't know this. And in the previous examples, this is what we've been concerned with learning about. So we saw that there was this conjugate prior. For theta, which was beta. And that's given some parameters. So these prior parameters, we're going to learn about those in some sort of prior elicitation. Some expert is probably going to give you some information on what they think theta is going to look like, and you're going to find some prior distribution for that. But what we want to learn about today, so we've already got what our likelihood is and our prior, and previously we've learned about what this posterior is going to be. But now we want to learn about what's going to happen when we have new data. So if we just have a single extra trial, of y, what can we say about that? Is it going to be a success or a failure? So we've already done, up to this point, we got that our posterior distribution, given some data x, was beta because beta is conjugate. So if we have a beta prior, we have a beta posterior. And it had these posterior parameters, which were, we take our prior parameter A and we add the number of successes that we saw. And we take our prior parameter B and we add the number of failures that we saw. So we've already done that bit. Now what we need is to do this predictive distribution. So if we look at what that concerns, it has this posterior, which we worked out in previous lectures. It's this beta distribution. And then we need what this likelihood of our data is. So our data y is a further trial. A trial is binomial, so we know that this is binomially distributed, just like what we did previously. So we can just put these into then our formula for our predictive distribution. So we want to know about this predictive distribution of what our future trial y is going to be, given the trials that we've already seen. And it's just going to be equal to this integral here. So we have this integral over theta, and we have the probability of what y is, given our parameter. So y is binomial data, so we just need what the binomial PDF is. You'll have already used it earlier on when you would have done your analysis to get your posterior, and you can always find it on your distribution sheet. So we have our PDF for what the distribution of y is, given our parameter. And then we need our posterior distribution of theta, which we've worked out here. So it's this beta distribution with these parameters. And if we'd have just done our posterior analysis, we'd have had that written down. If not, we can look on our distribution sheet to find out what that's like. And we get this integral. And this integral is going to be difficult to solve. So even if we group together our like terms, this still isn't going to be easy. So we're going to have to use this trick that we have about how to solve these integrals. Do we still have that? Yep. So we're going to use this process that we used in last Friday's lecture, and we're going to keep on using that again and again. So we need to find a distribution. If this is our g in this example here, where we want to find out this integral, then we need to find what is an f that is a PDF that looks like this, so that we can use this trick. So the f that we can use then, if we look at the kernel of this, there's a theta to some power and there's a 1 minus theta to some power. If we look at what kind of kernel of a distribution that looks like, it looks like a beta distribution. So we have this beta of some general parameters a and b. And that's going to be have a PDF of this kind of form. And what values then will we need to choose for alpha and beta so that that the kernel of this distribution looks like the kernel that we have in our own distribution. So if we choose alpha is a star plus y and beta is b star minus y, plus 1 because we don't have our minus here, then the integral over this distribution is going to look really similar then to the integral that we're looking for. But the key thing is that we know that the integral of this is going to equal 1. So we have the integral that we care about. And that's going to be equal to some constant times the integral that we already know the answer to. So that's going to be the integral of this PDF. So we've chosen our value for alpha and beta here. And then you can see then that we get the same thing. All of our terms of theta on the left-hand side that are in the integral are the same as all of our terms on the right-hand side. So we can just get rid of them, and we can just then work out what g is just in terms of these constant values in the same way as we would up here. So then g is just going to be equal to balancing at these. So we're going to get that. And we've already said then that the integral that we want to learn about is just equal to what g is. So the integral that we want to learn about here is just equal to g. So this predictive distribution of y is just equal to this fraction of beta distributions, which we can probably simplify but in terms of the bulk work, we've already done it. So that gives us what the probability of our future observation is going to be, given the observations that we've already seen. So we'll already have values for A star and B star, because we would have had values for our x, and we would have had our prior values for A and B. So we can work out what these are. These are just numbers. And then it's just this distribution in y. So it's y that's the unknown thing here that's changing. But because we only have one future trial, there's only two possibilities that y can take. It can have been a success, so y was equal to 1, or it can have been a failure, so it's equal to 0. So because there's only two possibilities, we may as well explicitly look at what they are, because we can do 2 by hand. So the probability then that this is going to be equal to 1, given the observations that we've seen previously, is just going to be equal to putting 1s wherever we see a y here. And if we go back to what this A star and B star was previously from our prior to posterior analysis, A star was the number of successes that we saw added on to A, and B star was the number of failures that we saw. And we know that beta distribution, the beta functions have this relation to gamma functions. So beta of A and B is equal to this function of gammas. And we can just plug that into this to get this really disgusting looking expression that's actually going to simplify quite a lot. And you can work through how to actually simplify this, but it's going to get to this expression. So you'll also remember that you can simplify gamma expressions because we have that relationship. So you can get from this line to this line quite easily. And that's then the probability of getting a success in this one future trial that we're going to be. The other possibility then was that we could get a failure, so that y was equal to 0. You can work through the exact same thing that we've just done here. Instead of 1s, you can put 0s into this, and you can work through and you can get all these gamma distributions and simplify them. It might be a good exercise for you to do that. But we also know that these are the only two possibilities. So if we have the probability of one of them, then we can just work out what the probability of the other is, because they're the only two possibilities. So it's just going to be 1 minus that. So we can just take 1 minus this expression that we've already worked out, which is going to save us time. And it's probably useful for you to do it both ways, just to prove to yourself that by working this out the long way, it is equal to this the short way. So that gives us our predictive distribution then. If we want to actually look at an example that uses that, we're going to carry on this GM sheep example. So we've just talked about one future trial. In this example, we're talking about doing an extra 10 trials. So you have an exercise in your lecture notes that you get to do, which is taking this example that we've just done, where we just have one future trial and extending it to having multiple. And that's left for you to do. So instead of having one future trial, we have m future ones. And then that exercise gets you to show that the predictive distribution of that is then this generalization of what we've seen here with just one future trial to having m. And you can see that these two things look quite similar. We've just generalized y being equal to 1, basically to being equal to m. And then we can actually apply it in this GM sheep example then. So we've got 10 future trials. And previously we had this data X, which showed us that we had X equals 13 successors out of N equals 30 trials. So they're just numbers. We've got 10 future trials, which is our M. And then our A and our B are going to be those prior parameters that we got from our experts. And whenever we've looked at this example before, we had two different versions of that, one from the company and one from the activist, that were quite different from one another. And you can see here that getting the form of what this is has just been done in R. So you've looked at the 10 possibilities for what Y can equal. So in this example above, when we just had one future trial, we just looked at the two possibilities of 0 and 1. Here we've got the 10 possibilities. And all that's happened is we've just, on this line here, we've just got what this distribution here is with the actual values that we've observed. And we can look at that in terms of a plot. So we get this predictive distribution. So if you'll remember, we had two different cases that we looked at. The first one was where we just had those 30 trials, and it was the 18 successes out of 30. And the posterior distributions of the two different people, the company and the activists, were quite different from one another. And we get the same thing here. If we put in our values for all of these quantities, then we get this distribution in. So we have 10 future trials. So Y can take one of those 10 values. And we get this distribution of the company and the activist of this predictive distribution. And they're quite different because everything is feeding down then from these priors. So because the predictive distribution has the posterior in it, and the posterior depends on the prior, then that's where you get this difference in what their predictive distributions are. But in the same way as when we got more data, so the plot on the right is when we had, instead of 30 trials, we had something like 1,000 trials. And we saw previously that in that case, the posterior of the two different people, the priors became less and less important because we had more data. So their posteriors became more similar to one another. And then we get the same thing here with the predictive distribution then. So the 2 points, they're not exactly the same. They weren't, because they didn't have exactly the same posteriors, but because these two things have got closer together, the whole predictive distribution of the two people become more similar to one another. So you can work through that, and you have this exercise to actually get to the point of what this is in the lecture notes, and you can look at how this has actually been plugged in to get those values. I think we will stop there for today, and tomorrow we're going to look at 2 more examples to do with exponential data.